I recently asked which of these regions correspond to the activation energy of the forward reaction in this chemical reaction. So if we take a look at this energy diagram, let's decipher what is actually going on here in general. So we have our y-axis, and that corresponds to the potential energy of whatever species we're talking about, okay? And then the x-axis is labeled the reaction coordinate. And what is reaction coordinate, right? Well, it's basically where you are in the reaction. So, you could think of it as like time. As we go forward, we're progressing through the reaction. But of course, in real life, in a reaction at any moment, you can have reactant, product, and transition state material all at the same time. So that's why we don't call it time. We're just saying it's the reaction coordinate, like where in the reaction are we? Are we looking at the reactants? Are we looking at the transition state? Are we looking at the products? And so it's just basically reaction progress is another way to think of it. So now, what do each of these regions correspond to? Well, if we just look at region A here, it's going from the x-axis up to the potential energy of the reactants. So just whatever the potential energy of A and B are combined, that is what region A stands for. It's the potential energy of the reactants. And then so we have our reactants. We have to add energy to them to initiate the reaction, to activate the reaction. So how much energy in order to activate it? So we have to get up here to our transition state. And that's basically where the bonds are being formed and broken. And so this is a higher energy species. And so that's why we have to get up this hill in order to get the reaction started. And that is our transition state, like I said. And then we are going to be releasing energy, and we get down to the potential energy of our products. Okay, so now, which of these regions correspond to the activation energy of the forward reaction? Well, before I solve that, guys, I just want to mention, if these videos help, please give a like, follow, share this with someone else that could use the help, save it so you can review it again later, and consider supporting me and patronizing me over here on my upside down link. Yeah, I just needed more room on my board. I flipped it around. Anyways, guys, so again, check out my stuff over here. Please support, and let's continue. So if we're looking at B, this is just the actual potential energy of the transition state. But it's not the amount of energy required to activate the reaction. That would be the energy to get to the transition state minus where are we starting from. So we're already starting here at this potential energy, this value. So then the difference between the top of the hill and your starting materials, that region D here, right? So it's this potential energy there minus this potential energy here. That's going to give us our activation energy. And in this case, I'm referring to the reactants, so it's of the forward reaction. So D is the energy of activation, and I'm going to put an F here because it's for the forward reaction, okay? So activation energy is always represented by E sub A, energy of activation, and then I'm putting the F there to indicate that it's for the forward reaction. Because I do want to know also what will be the activation energy of the reverse reaction, okay? So as we're continuing on here, you can go ahead and comment that down below and see if you're right. We'll get to that in a minute. So now, let's look at some other things involved with the reaction. We have our starting materials here. We add energy to get up to the transition state. All right, we add our activation energy. Now, it's kind of like we rolled the rock up the hill. We put in the energy to get it going, and now that we got it started, the rest of it is just going to take off. So the rock is going to roll down the hill, and the reaction is going to take off. So it's like, getting everything set up, you need to add energy to get up there. And once you get up there to that transition state or the top of the hill, it's just going to go on its own now. And so once we are here, we're releasing energy all the way down till we get to the products, C and D. Now, what is happening here? We have this amount of energy when we start, then this lower amount of energy when we finish, right? So that means that we're releasing energy when this reaction occurs, in this particular case, in my example here. So as we go in the forward reaction, this amount of energy between the potential energy of A and B combined to the energy of C and D combined, this energy is the energy of the reaction. Sometimes you'll see this written as delta H, which is enthalpy. Other times it'll be delta G, which is the Gibbs free energy. It's the same idea basically, Delta G gives you a little more information, but it's the same idea. If we have our reactants are here, our products are here, the difference in energy is going to be the energy of our reaction, and I'm just going to use delta H for this. And so that's the enthalpy. If A and B are higher than C and D, then that means energy is going to be released, right? We started with more energy or more highly energetic starting materials, and we ended up with lower energy materials. So that difference is just released into the environment. And that's our delta H. So this is going to be a negative delta H, right? Because it's going to be the energy of the products minus the energy of the reactants. So that's going to be a lower number minus a bigger number, and that gives us a negative delta H. So this is exothermic. And that's a great question that you might see. Is this reaction endothermic or exothermic? In this case, it's going to be exothermic for the forward reaction. Now, let's switch things around. Let's look at the reverse reaction. So I could just like redraw this, like the mirror image basically, but you may also see questions written about the reverse reactions. So let's look at that. Now let's say we're starting at C and D, right? We have a reversible reaction. I could either give you A and B and they react to go make C and D, or I can give you C and D and they're going to react to go make A and B, right? And so let's look at the reverse reaction for starting with C and D. How much energy is required to get the reaction started? In other words, what is the activation energy of the reverse reaction? Well, we have to go from wherever we're starting to the top of the hill. So the amount of energy from C and D up to the peak, which is this is going to be the energy of activation for the reverse reaction. Ear over here. That is the activation energy of the reverse reaction. From wherever you're starting up to the top of the hill, that's your activation energy. If you're going this way, it's from this level up to the top. If you're going forward, it's from this level up to the top. Activation energy to start the reaction. Now, we get up to the top and energy is released from the transition state, but not as much as when we go the other way. It's actually the exact opposite, right? In other words, we have to roll the rock up the hill, and that's going to roll down the hill, but it's going to end up at a higher location, a higher altitude, or a higher potential energy here in the physical real world. So in other words, this difference of energy is still going to be our delta H, but now it's the energy of the products minus the energy of the reactants. So this potential energy minus this one is now going to be a positive number. So we can say that the reverse reaction is endothermic. You have to add energy to get this reaction to happen. So, of course, you have to add enough energy to get up to the transition state, your activation energy, but then the net energy of the reaction is positive. So that, in other words, if you had this reaction happening in a beaker, you're going to feel it get cold because the compounds are absorbing energy. They're absorbing heat in order to become these other compounds or these other substances. And so knowing it's exothermic or endothermic is going to be an important question that you might see by looking at these energy diagrams on an exam. And so basically, if we're just looking at the forward reactions, if your starting materials are higher than your products, it's going to be exothermic because you're releasing energy. And if I drew this the other way, where it went up and then, let's just say that it finished like over here, right? Now, if this was C and D, now our products are higher energy than the reactants, so that would be an endothermic reaction, okay? So the way I originally drew it was exothermic. If it went up and ended here, that would be endothermic, okay? And then we already talked about the activation energy of the reverse reaction. I think that pretty much does it. Is there anything else that I want to mention about this? Oh, yes. One more thing is the effect of catalysts. So a catalyst does not affect like equilibrium concentrations, which I will be talking about probably in my next lesson. But what it does is they speed up reactions. Catalysts speed up reactions by providing an alternate mechanism or an alternate pathway of the reaction, which has a lower energy or a lower activation energy. So in other words, instead of having to go from A and B and rolling the rock all the way up to the top of the hill to get down to our products, And let me just get rid of this alternate one over here. Instead of having to roll it up that high, and it's going to take us more time to get it up there, we have to add more energy to get it up there. If we have a catalyst, it's like basically digging a tunnel through the mountain or through the hill here. And so now a catalyst would provide an alternate pathway that's going to start and end up in the same location, but it will be a lower amount. So we're going to have a lower activation energy when we have a catalyst provided, okay? And so now the activation energy of the catalyzed reaction is going to be from the top of the mound to wherever our starting materials are. So this would be activation energy of the catalyzed forward reaction. And so that's that there. All right, guys, if you have any questions, go ahead and comment them down below. Or if you have any requests for other lessons that you want to see, go ahead and comment that. Again, please support the channel, and I'll see you guys in the next one.